All right, well, welcome. Welcome to Cool Jobs. You guys having a good time so far? Yeah. All right. How many have been to Cool Jobs before? All right, so we got some. If you've never been here before, basically, we show you some people that use science in their everyday jobs to do some pretty amazing things. And more important than that, we want to give you an idea, especially if you are on the younger end of our audience, of jobs in science that you might not have thought existed before that you guys might want to follow. So we're going to have some fun. You're going to learn some amazing new jobs. And I have a new sidekick. I don't know if you've noticed. This is our new sidekick, 11. This is 11. How many of you are fans of Stranger Things? All right, nice. All right. So 11, of course, has many, many talents, and as does our robot friend, and that's how it got its name, 11. Believe it or not, this cool robot was built by a bunch of 7th graders at the St. Clair School, and so they are here today. We're going to talk about them a little bit more later. But 11, I am told that you have a gift for me. What do you got? Oh. Go ahead, you can applaud the robot. Yeah, there we go. Let's see. Oh, I get it. See, this is a parachute. See, it's a little parachute ball. Now, you might not think that parachutes, there's a lot of science in parachutes, but can you actually have a job in parachutes? Yes, you can, but imagine, instead of a plastic ball being at the end of your parachute, there's something that costs $2 billion. You want to have a good parachute artist and a science person running that. And that leads us to our very first cool job presenter. From NASA's JPL laboratories, please welcome parachute scientist Mike Meacham.
Hey guys. Thanks, thank you. I'm Mike Meacham. Yeah, that's a photo of me at work. That's what I look like when I do my job. We do some crazy things at JPL. It's a NASA center in California called Jet Propulsion Laboratory. We're known for robotic exploration of the solar system. We like to figure out what our solar system is made of, and since it's so difficult, at least with today's technology, to send people, we send robots to do it for us. They sample other surfaces of planets, and they send us back the information. One of our favorite places to go is Mars. We love sending things to Mars. We send primarily rovers to Mars that can actually wheel themselves around. Some of you guys have probably seen Curiosity. It's up there now. It's been up there for years now, taking good samples of the soil and sending us back data. It is difficult to land things on Mars. When we approach the planet, we're going more than 10,000 miles per hour, if you can get that in your heads. It's extremely fast. And our job at JPL is to go from 10,000 miles an hour to 0 miles an hour. That's it, right? And you have to do it in about 7 minutes, otherwise it's game over. You'll hit the surface way too hard. So I want to show you a part of this very complex sequence now. There's an animation that kind of shows how Curiosity landed. There's a huge parachute deployed, slowing our spacecraft down. The next thing we do is kick the heat shield off, exposing the rover to the surface so it can actually start seeing it. The rover slides out of the back shell, and we fire up our rockets, and it's actually a rocket-powered elevator that lowers the rover down to the surface. We call this the sky crane maneuver. It gently, fingers crossed, deposits the rover onto the surface. We cut away that elevator portion, and it literally flies away and destroys itself. And the last thing, the only thing that hasn't crash-landed, is the rover itself. It's a very complicated sequence. The scariest part of that, at least for me, and a lot of people I work with, is that parachute inflation. The parachute is really big. It has to inflate at about 1,000 miles per hour. You don't find that very often here on Earth. And it has to take enormous amounts of force. The parachute weighs about 100 pounds, but it has to take 60,000 pounds of force, if you can get that in your heads. It's a lot of force. If it fails, we crash. It's as simple as that. We only have one parachute. There's no time to change things up. This is all autonomous, which means we can't talk to it. It has to do it on its own. So it's deploying the parachute when it thinks it's right to deploy it, and if it bursts, it's game over. So what that means for me and my team is that we have to test this parachute. We have to test it really, really well so we gain confidence that it won't break at Mars. And that can be really tricky. I want to talk about testing parachutes a little bit today. But before we get into testing, let's learn a little bit about parachutes themselves, okay? So you probably noticed this ridiculously big fan behind me that I brought. It's a really high-powered fan, and it's gonna help us learn how parachutes work a little bit. I brought 3 parachutes with me today. The big difference between them is their size. So I got a little tiny one, I got a medium-sized one, and some of you can probably see I've got a very large one on the stage here. What I want you to pay attention to, it's going to be hard to hear my voice once we get the fan turned on, but what I want you to pay attention to is how the larger parachutes cause more force. The fan is at one speed, same wind, bigger parachutes, much more force, okay? So with that in mind, let's fire up this fan and we'll start playing with parachutes, right? Fire it up. Okay, it's a little parachute. It's a NASA teddy bear. Not hard to hold on to. There we go. Yeah. All right. Medium parachute. Ah! Cool. Whoa! That's a lot more force. All right, right on. So should we test the big one? Okay, for the big one, I'm gonna need help because it's a lot of force, right? Same fan, big parachute. So we're gonna bring in people. We need 4 people to hold this thing down, okay? You guys ready? 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 Thanks. Awesome. Okay, so that's a big parachute. These guys are working hard back here. I'm gonna see if I can get them just to walk forward a little bit so you guys can touch it, okay? You guys just wanna come forward together? So you can feel free to touch it, it won't hurt. It's just nylon like you'd find in a camping tent. Let's bring it back. And let's kill the fan. All right. So everyone gets the basic idea, right? Bigger parachutes, more force. Not so hard. Our Mars parachute is about twice the size of that parachute. That's the one that landed Curiosity. Thanks, guys. What we basically just saw here was a wind tunnel test. We just tested 3 parachutes, not to super high forces, but they're tested. We know they work somewhat. But for Mars, we need to do a lot better than that, right? So for Curiosity and previous missions, we've gone to wind tunnels. There are wind tunnels in this country that are much larger than this room, thousands of times more powerful than that fan, and they can blow wind at 100 miles per hour consistently down a huge tunnel, and we can inflate our parachutes and test them to the same forces that they're going to feel on Mars. Now, you heard 100 miles an hour and 1,000 miles an hour. What's going on? The atmosphere at Mars is very, very thin compared to what you're feeling in this room now. This air is it's like molasses compared to the air on Mars. It's very thick here. So when a parachute inflates on Mars at 1,000 miles an hour, it produces a certain amount of force, and to reproduce that force here on Earth, you can go slower and get the same amount of forces. And we use that to our advantage in testing. So 1,000 miles an hour at Mars equals a little less than 100 miles an hour here at Earth. Here's the big problem. We want to land bigger things on Mars, which means, inevitably, you need bigger parachutes. And the problem we're running into is that these bigger parachutes don't fit in any wind tunnel that exists today. And it's very expensive and complicated to build new wind tunnels. We have to test these parachutes. Everything's riding on them. $2 billion, as Bob says. It's a lot of money. A lot of science goes into this. We don't want to fail the mission, so we are going to test this parachute. We have to find a way. This was a question posed to me and my team. They said, find a way to test this parachute, even though you can't use a wind tunnel. So what would you do? How do you pass 100 mile per hour wind over a parachute if you can't use a fan, you can't use a tunnel, and you can't build a tunnel? We don't have the money to build a new tunnel. So we started drawing on the whiteboard. We came up with all kinds of crazy concepts. And long story short, I'm going to show you guys what we eventually came up with. It starts with a helicopter, a very cool Nighthawk helicopter. Right now, it's picking a parachute up off the ground. It's inside of a bag. On the bottom of the bag is a kilometer of rope. This rope weighs 3,000 pounds. It's a whole kilometer stretched across the desert floor. The helicopter flies up, a kilometer in the air, The pilot releases the parachute, and we start spooling in that rope with a high horsepower winch, a 300 horsepower winch. You can see up the top of this video here. So we're maintaining tension in the line. And we pull the parachute down, we pull it down, and we latch it up to the back of a rocket sled. A sled that's powered by huge rockets, hundreds of thousands of pounds of thrust. What's going to happen is that winch is pulling it down, it's going to latch up into the back of the sled, and it's going to automatically trigger the rockets to pull the parachute around a pulley. Boom, right? So that sled starts taking off. That's a huge sled. It's over 100 feet long, more than 100,000 pounds in weight. We had to pour 2 million pounds of concrete into the ground just to hold this parachute in place. And you can see we're getting over 90,000 pounds of force on this parachute. You're probably also noticing the parachute ripped. Oh no, right? We're going to crash at Mars. That's why we do this test. That's why it was so important to come up with it, is that if we don't do a test like this and we just think we have the parachute figured out, we will fail a mission. So it's important to figure that kind of stuff out. So that's what I kind of do in my career. I think of crazy ways to test our technologies. If you're curious about where I came from, how I got into this sort of career, I'll tell you a little bit of the background of myself. I studied mechanical engineering at school, in college. To me, mechanical engineering just means you're using the things you learned in science and math and applying it towards building something. It's as simple as that, right? Don't just build it and guess. Use your formulas. Use the things you've learned in class. And you're much better off that way. So what did I build in school? I always loved building things that I could ride. I like building things that no one had built before that I could get on somehow and go for a ride. So I love mountain biking. There's me on my mountain bike, and I wanted to see in college if I could ride a skateboard down the same trails my mountain bike was on. So I built this off-road skateboard. I'm hurting myself in this video pretty badly. And it worked great, and I love building that kind of stuff. Another thing we do for fun sometimes, my friends and I, we try to come up with really crazy concepts. Also, we're engineering these things. Here's 4 weather balloons we inflated. We strapped it to a climbing harness, and I jumped off a roof with that. And it's safe. See, I'm okay. And the reason I'm okay is because I used all those formulas. We knew the buoyancy calculations. We knew the drag forces. We knew how to keep ourselves safe. So that's kind of the nutshell about what I do in my career. If that kind of thing interests you, just pay attention in math and science. That's all you got to do, and just keep trying hard. Thank you for the time.
All right, Mike Meacham. See, here's what I'm saying. Who knew that parachute engineer was like a job you can have? How cool is that? All I know is if I go skydiving, I want Mike packing the bag, because that's going to work. Oh, we got 11's back. Hey, 11, what you got there? Oh, you got a ball. You got another ball. I didn't know that you could pitch, but let's see what you got. Nice, nice. All right. Now, how many of you guys are sports fans or play sports? Yeah, I've had kids that have come to me and say, yeah, I like science, but I'm kind of more of a sports kid. Well, let me tell you. If you know a little bit about science, you can be a really, really gifted sports kid, because there is a lot of science that can help you out. In fact, I know a mechanical engineer and a computer scientist that are going to show you just what you can do. From Pittsburgh, Pennsylvania, please welcome Buddy and Mike.
Hey, everyone. So my name's Buddy Clark, and I actually have 2 cool jobs. First, I'm a professor of mechanical engineering at the University of Pittsburgh, and I get to teach a lot of students, like Mike, how to design and build some really cool things in their careers. Secondly, I'm a founder of a sports tech company called Diamond Kinetics, where I get to work with some really smart people like this Mike to build some of our own really cool things. And that's the story we're going to talk about today. So I'm going to start back when I was little, same age as some of you. I grew up in Virginia in the mountains on a beef cattle farm with my 4 brothers and 1 sister. And if you know anything about cattle, they like to eat a lot. And so we had to harvest a lot of food for them. And so most of the time, I got to work with equipment like this to harvest the equipment. This is obviously a tractor pulling what's called a corn chopper, and that's me in the cab with my girlfriend at the time, who's now my wife. So I love the equipment. I loved learning how it worked. I loved operating it, and I loved figuring out how to fix it when it broke down. The only thing I really didn't like was cleaning it and maintaining it. That was kind of a necessary part of the job. So the other thing that we did a lot of when I was growing up with my brothers was we played a lot of baseball and softball, or baseball for us. And I loved the game. And little did I know that at some point in my career, I could take those passions of the mechanics and the machinery and the technology and the sports and all of my math and science knowledge and put them together in a sports tech company.
Hello, everyone. I'm Mike Ressler. I'm the Chief Technology Officer at Diamond Kinetics. I have the greatest job in the world. I get to play with baseball and also do some really cool science and technology as well. So I'll tell you a little bit about myself. I grew up in East Brunswick, New Jersey, not too far from here. Played a lot of sports when I was in East Brunswick. Baseball ended up being my first love, my first sport. So you'll see a picture here of me getting to go to a lot of Phillies games. So Phillies was my family's favorite, so there was me. Became my favorite sport. Kind of interestingly, every time I would go to these Phillies games, my dad would let me eat as many hot dogs as I possibly could. So that was super fun for me, and it was a really easy way for me to love baseball. I did actually play, though. I didn't just eat hot dogs at games. So here's a picture of me at Little League, braces and all, way back when. So I did play quite a bit. Then beyond Little League into high school, I found that I could make computers do really cool things for me, and I could make them do pretty much anything that I wanted to. So being a very lazy high school student, I decided to work really hard and teach the computer how to do my homework for me, which was fantastic. And I got to be very popular in Mrs. Gulick's algebra class, as that program was a hit among all my friends. So then beyond high school, I had a choice to make. So it was now going into college, do I try to get an athletic scholarship, or do I try to go into academics?
And so Mike likes to say he went the academic route and he became a Division I nerd.
Which is true. So I got to go to Carnegie Mellon University, School of Computer Science. I was privileged enough to get in. It was fantastic. Really enjoyed my time there. And then I did some software engineering for quite some time, which was a lot of fun, but it wasn't until I did both my sports side and my nerd side together that I really found that I loved what I did.
So I went to school at Virginia Tech and then finished my degrees and started teaching at the University of Pittsburgh, where my wife and I started raising a family. We have 2 daughters, 1 son, and I have my 2 daughters with me today, Alyssa and Renee. They're going to help us demo some of this.
And I would love it if I could show you guys Buddy's basement. He actually custom built his house so that he could have a full-size batting cage in his basement. True story. So obviously his love and passion for the game of baseball has transcended and has gone to all of his children.
That is true. The kids didn't have to go far to go take hitting lessons. We have part of that cage here today. We've got a screen set up that we'll hit and throw into. And one of the things that my wife and I focused on, we're both scientists, so it wasn't just enough to coach. We coached all of our kids in the game. Here's a couple pictures of my wife, and there's Alyssa a few years ago. And then there's another picture of me with Renee's team, and Renee's just a little bit younger than she is now. But we coached them all the way from T-ball up to college age, and we were interested not just in the coaching, but just in the physics of the game. You know, what were the right motions? What's a good swing? What's the right bat to use? There's so many bats to choose from. And it turned out to be a difficult thing to answer.
Yeah, it's amazing for a sport that's 150 years old, like baseball, that we wouldn't have more answers to those questions sort of readily at hand. But the swinging motion of baseball is so fast and so powerful that traditional and other methods of collecting and analyzing that swing are not easily available to everyone. So that's what we're able to put together.
That's right. So we're going to actually do a demo, and we're going to test ourselves and see just what we can see from our own eyes about the swing. Alyssa's going to take a swing, and let's see what we can pull from it. So pretty good swing, right? Let me ask you this. So let's talk technical here for a second. How fast was it? What angle did it go at? Was it a good swing to produce a home run or a base hit? That's really hard to tell, right? Now that we know what to look for, let's do it again and see if we can detect some things. Another pretty good swing, right? So again, it's really hard to see all the details from just our eyes. And that's the only tool we had for years. In fact, other tools that were available, really expensive, really complicated, high-speed cameras, difficult setups. We were looking for something that was relatively simple. And so I've worked on this for years in my basement testing, and with this company, we've developed some of that technology. It's compact, it goes right on the bat, and without getting into too much detail, it kind of acts like magic. It takes information from the bat, sends it over to an iPad, and displays a lot of details about the swing. So we're going to take another swing with the sensor in place and see what we get. Another good swing. Alyssa's on a roll here.
There we go.
Thanks, Alyssa. So this is the information that gets transmitted from the sensor that Mike just put in the bat. And let's look at a couple details. There's a lot of numbers there, but not to get into too much detail. Look at the far left number on the bottom, 63 miles an hour. That's how fast the barrel was moving at its peak speed during the swing, right? We can relate to that. Speed limit on the road a lot of times is 65, right? That's how fast Alyssa's barrel was moving. Was that good, bad? What can we tell? We can actually predict, we can measure or calculate from that speed, if she squared it up, how far the ball would travel. And that's why that white band lit up. So she could have hit that ball 248 feet. That's actually over the fence for most college softball parks, right? So good job, Alyssa. Let's do it again. Take another look. See what she's got. Did she do better?
Let's find out.
See if it pops this one up. Actually, I don't know if it got that one.
Didn't see it, but that's
change.
right.
So anyway, we can get all that neat information. And again, it's kind of like magic, but we know it's science and math here.
Yeah, man. So one of the things that we can do with all of that very accurate, very precise, fast streaming data off of that device, we can actually recreate a full 3D of the swing. So we can slow it down and see every little nuance of that swing. What did Alyssa do? What was she swinging up or swinging down? We can see it from every single angle, which is super useful for coaches who are trying to teach their players and players who are trying to get better at the sport of baseball. So it's pretty wild. It seems like magic that we have this tiny little chip, this tiny little device, but it can do all of this.
Yeah, so how does all that work? I'm going to show you the details here. This is the actual sensor. If we look at a close-up, there's a little LED flashing in there that just tells us that it's on and it's communicating. And Mike will tell you a little bit of the details about what's inside of this thing.
And the other picture that we saw up there is a picture of the actual chip itself. So on that green circle that you saw, those are the electronics that are inside that flashing device right there, right? So that's everything that it needs, microscopic components to both record and store and transmit all of that fast motion over here to the iPad, which is pretty amazing.
But we didn't stop there. We thought, you know, maybe there's other important motions in baseball and softball that we would like to measure. So can you think of anything that might be of interest? How about the throw? How about the ball movement, right? Let's not just focus on the hitters, but maybe the pitchers really want information as well. So we took that same sensor, buried it deep inside a baseball, so the baseball looks and feels exactly the same leather, same threads, same weight, and we can now measure the baseball throw. So we've got a special guest that's going to help us with this. So I want to introduce Gemma from Brooklyn, who's here with us today. Hi, Gemma. Hold the mic up. So Gemma, as you can see, is a softball player. She's dressed for the game. In fact, you have a game later today, and you have to rush out afterward, right?
Yeah.
All right. So she's second baseman, right? And you're a good student in school. You like school?
Yeah, I do like school.
What's your favorite subject?
Writing or science?
Writing or science, cool. So you're at the right place here. So, what do you think you want to do with all that when you grow up?
I want to be a writer or a museum
That's okay.
Curator.
Curator, a writer or a museum curator. Maybe even you can put those two together.
Maybe.
Write some articles for magazines, for museums or something, right?
That would be cool.
All right, well, we know that you have an important game to get to, so we're not going to hold you up long. But if you could, and we really appreciate you coming out here to do this for us, we want you to throw some balls to Alyssa. She's all geared up to catch now. And we're going to see if the sensor inside that ball can actually measure your throw. So stand over here and do it just like we talked about. Hold it still, and then throw it. All right, thanks, Gemma. Let's try it again. I don't know if we were able to get that one, but I want you to hold it still. And when you're ready, give it a good hard throw. All right, good job. I think we threw a strike on that one. See if we got any numbers off of that.
No.
So sometimes
Coming up.
the sensor's looking for motions, and if it doesn't see exactly the right thing, then it thinks that wasn't a throw, or if it wasn't hard enough, or maybe she wasn't moving it exactly like what a throw looks like. Let's do it one more time. Good. You're just pumping the strikes in there. So see if we got anything on that. I don't know if we're going to show anything.
Yeah,
There we got it.
All right.
All right, good job. So let's see what we showed. 36 miles an hour. So you threw the ball 36 miles an hour. It had a spin rate of 883 RPM. So why does that matter? Obviously, those are different numbers than the swing, right? Because the motion's different. We would expect to see different numbers. And the speed matters because the faster you throw the ball, the more likely the batter's going to miss, which is what you want. And the more spin you put on the ball, the more air force is applied to cause it to curve, which also makes the batter miss. So Gemma can then use these numbers to train and get better to make her pitches better, if you were a pitcher, right?
But buddy, there's a problem here. Gemma doesn't actually throw baseballs. No.
You don't throw a baseball?
Nope.
What do you throw?
Softball.
Of course you do, right? You're dressed for softball. Well, if only we had a softball to throw, and you happen to have a softball. Yeah, we sort of planned this. So we have taken that same technology, and actually just recently, we've put it inside a softball. In fact, this is only about 2 weeks old. So this is a real treat for us, and I hope it's a treat for you. You are going to see the very first demonstration in the world of a smart softball. And I get to do it with my daughters who were softball players. So Renee is going to throw the softball to Alyssa. You ready, Mike?
No, let's give it another twist. It actually didn't turn on, so I'm going to do one.
So there's no buttons on the ball, right? You can't turn it on. So it has to wake up in different ways. We have to sort of engineer in ways like that to tell it to wake up. And that's what Mike just did. And so after it's awake, it's now measuring every single motion that it sees, and then it looks for a pitch. And we'll see if it detects Renee's pitch. You good? Hang on, let's make sure Mike's ready. Is it attached and awake?
Yeah, there we go.
Are we good? All right, Renee, throw a strike. There we go.
There we go.
I think that was the strike. And that pitch was obviously 45 miles an hour. Oh, 40 miles an hour. I think it did get the last one. We just
came in together.
And 641 RPM. It's a different release, different spin. All that stuff's different. And I do appreciate. Renee's done this before, so she pitched in high school, and Alyssa actually caught in college. So I knew I could trust them to do it. So.
And it's pretty amazing that that same sensor, that same equipment that we saw, that circle, that green circle, that very same sensor with a little bit of extra hardware that Buddy's team does, a little bit of extra software and firmware that my team puts together, we can compact that in, put it into a ball, and do the same hardware, but it gets to read both the swing and the pitch, which is pretty amazing. So the takeaway from all this is I hope everyone gets as much as they possibly can out of their math course and out of their science course and really enjoys it. But please don't forget about the hobbies that you do, all the things that you really love and enjoy at home. All of those things are super fun and great. And I do hope that everyone here today is able to, at some point, do what they both love and what they're good at together, like all of us have. Thank you.
Thank you.
All right, I don't know about you, but that kind of blew me away. Like, you put something the size of an Oreo on a bat, and it gives you all that information. That's like science fiction to me. I also know that I would love to be on his team, but I wouldn't want to play his team. All right, well, hey, look, 11 is back. 11, you look like you're ready to solve a mystery. That's kind of cool. You know, I should also introduce our robotic team here. I don't know what you were doing when you were 12, but I know I wasn't programming Lego robots. So I do want to, guys, come on out here. Let's meet the team here. We've got Giovanni, Louis, James, Dean, and Domenico, the St. Clair Transformers team. Awesome. I will also point out, we gave them like a week's notice about this, and they had to customize their robots to do what we wanted them to do, and they came through with shining colors. So thank you, guys. Thanks. All right. So speaking of mysteries, how many of you guys like reading mystery books or watching mystery TV shows? Yeah, I'm a big fan of mysteries. Well, of course, solving mysteries can be a very, very cool job. Sometimes a little slow, it's all right. And so then if you want to solve crimes using science, you become what's known as a forensic scientist. And so we happen to have one here today to talk about their cool job. Please welcome Casie Parish Fisher.
Hi, everybody. Hi. So good to be here. So my name is Casie Parish Fisher. Even though my Star Wars fans, if you feel like calling me Carrie, it's the second time, Bob. Second time. It's all right. I think it might make me a little more popular that way. So I grew up in a small town in East Texas. When you think of Texas, what do you think of? Tell me. Cowboys, right? Do you expect me to have a cowboy hat on? Cowboy hat on, some boots? Well, I did grow up in a really small town in Texas. My grandparents, my great aunt, they all have farms, and of course we have animals, right? What kind of animals do you think I would have? Cow, right? Not exactly a cow. I was a big fan of lambs and pigs. My dad, who is very protective, thought a cow might be a little bit too big for me. So lambs and pigs it was growing up. But I was lucky to have fantastic parents who really supported what I did growing up. My dad was a police officer. He was a commissioned officer in the state of Texas. So he went out and he did a lot of community work to serve our community, which was great. My mom was a banker. Huh, right? And I thought, yeah, a banker. That's what I want to be because you get to spend the money, right? You get to go shopping because it's a bank. It gives you money. Not exactly how it works. Once I found out what she did, she just kind of monitors the money. You don't actually get it. So I started hanging out with my dad a little more, went on some ride-alongs, and realized that, wow, this police work could be interesting. But I didn't want to be a police officer. I didn't want to have a gun and a badge and write tickets and that sort of thing. And I loved science as I started going through school. So chemistries and biology and genetics, that was more my forte. So going into college, I went to Baylor University, and I ended up getting a forensic science degree there. And I thought, great, crime scene is what I want to do. How many of you love those TV shows? Law and Order, CSI, the list goes on and on and on, right? Glamorous. I was going to be in a cute outfit. It was going to be fantastic. Great shoes, cool car, right? The Hummer. That's what everyone knows. But it wasn't exactly that way when I started to work. Texas is really, really hot. Like we're already in 100-degree temperatures there already. And so I thought, I think I should transition and go into the laboratory where it's nice and cool and air-conditioned. But I learned a lot while I was doing my crime scene work, particularly in the form of fingerprints. So fingerprints, they're all on our fingers, right? Everybody has fingers? Very good. If you actually take your thumb and your forefinger and you kind of rub it really lightly together, you almost feel like a texture or ridges on your fingers. And that is what we use to identify you. They're unique to everybody who's in here. So we're going to do a little experiment. This is something you can actually do at home. You don't have to have a fancy laboratory to do some of this stuff. So I'm going to have some helpers come up. Who are my volunteers to come up and help me? We are going to play with some fingerprints on balloons. Round of applause for my helpers. Very good. What's your name? Gabriel. Very nice to meet you. Brandon. Very nice to meet you. Helene, very nice to meet you. All right, we are gonna station right behind here, and we are actually gonna use balloons to blow up our fingerprints and see what characteristics we have. So, everybody ready? So we're gonna take our balloons in our hands, and we're gonna inflate them just a little bit. Don't blow them all the way up. And then we're gonna twist it so the air doesn't come out. Are you ready? All right, I'll do it with you. And twist. Very good. Perfect. All right, so now we have ink pads in front of us. Anything that you can use pens if you don't have ink pads at home. We're very lightly gonna touch our finger on the ink pad and just get a little bit of ink on there. Just a little tiny bit. Everybody got a little bit of ink? Perfect. Now we're gonna set our balloons on the table. And we are gonna mash our fingers straight down and right back up. Very good. All right, we have little wipies. Oop, little wipies are down here. We'll wipe your thumb off really quick. Excellent. There you go. And now we are actually going to blow our balloons up. And when we do, it's nothing like having 200 people watch you blow up a balloon, just so you know. No pressure at all for me. All right, so once we blow up our balloons, you can actually see, we'll hold these for our camera guy really quick, that you can actually see the different characteristics that are in your fingerprint. So very much like looking at this nowadays on your cell phone or a computer, a balloon and some ink will do the same thing. There are lots of different patterns and characteristics. Let's see what yours is. Oh, very good. Can you hold yours for our camera guy right there? Perfect. There are three major categories that we look at in regards to fingerprints: loops, whorls, and arches. So loops are the most common. You have ridges that come in from one side and then turn and go right back out the other. Those are indicative of loops. If you have a whorl, it kind of spins around in a circle, like a hurricane spinning in the Gulf of Mexico, close to Texas where I am, spins around. And then arches have ridges that come in and they go right back down. Arches are the rarest. So if you have an arch on your finger, then it's pretty rare. About 5% of the population has that. Very good. All right, now we get the fun part. You get to let the air out of your balloon. Ready? Nice. Oop, you tied yours off. Very good. A round of applause for my volunteers, please. Thank you. So the fun part about forensic science in general is generally we're looking for things that you can't see, right? They're not visible to the naked eye. So sometimes we have to use chemical processes to be able to visualize these things. If it's on the surface, generally there's a lot more. So with fingerprints, we could put our fingerprint on the balloon and we could see the ridges. But what you didn't see was the deposit that we left behind. So we're always shedding cells, sweat. Was it a hot walk here? Hot walk here, hot outside? Sweat coming off. And all of that is depositing biological evidence. What's another type of biological evidence that's really, really common? Anybody want to guess? Blood. Blood is the most common. So we actually have a chemical that we can use to be able to visualize blood in a scene that you can't see with the naked eye. So I have 3 tiles here, all set up. Do you think they have blood on them? Yes, no, maybe so? Yes, yes. All right, let's find out. So if I can have my scientists come join me here, we are going to use a chemical called amido black. This stains the proteins in our blood. It just comes in a little spray bottle that you can spray on it. Very good. And then we have a water bottle here where we can rinse it off. We're going to rinse off the amido black. If it's truly blood on our tile, then it will have this blue-black stain on it. And if it's not, if it's something like dirt or ketchup that you may have spilled, then it won't react at all. You won't be able to see anything. It'll just clear it right off. So if you guys want to take your spray bottles, Step back arm's length. There you go. And you're just gonna spray, 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 and cover the whole tile. Make sure it's nice and coated. Also, in full disclosure, this is cow blood. No humans were harmed in the course of setting up this activity. So cow blood will react the same. It still has proteins in its blood as well. We use that for a lot of our tests and forensics. Whoops, very good. Maybe turning purple myself. All right, very good. Now we want to take our water bottles and we want to rinse it off and see if we can see anything on there. Yep, just rinse it all the way. Very good. All the way down. Very good, very good. So, does anybody see anything on their tile that could possibly mean that they have blood on their tile? So tile number 1, do you see anything that may be blood on your tile? Or does it look like it's all coming off? Yep. A little bit? A little bit of blood on there. How about tile number 2? Helene, you got it there? Very good. So yeah, we definitely have some blood spray there. All right, what about tile number 3?
Not so far.
Not so far? So very good. Yours actually doesn't have blood on it, so you're right. Very good. All right, thank you guys so much for your help. Very good. So these chemicals are great for when we're working a crime scene in an area that's lit, and it's ambient light. We have plenty of lighting. We can see everything that's going on. But what happens when a scene is burned? Does that complicate things maybe just a little bit? Just a tiny bit? If I were to use this Amido black that turns our blood stains black in a burned arson scene, would I be able to see anything? No, because everything's already sort of turned black. So part of my research now has sort of transitioned into helping arson investigators. What do arson investigators do? Anybody want to guess? Go ahead, tell me. Very good. So they're firefighters who specialize in working crime scenes that are burned. So my research now has transitioned into recovering DNA from fire scenes. So for example, we have this plate and a piece of paper in it, which is going to represent our scene. Usually when we think of a fire scene, I'm going to attempt to light this. Oof. We have a fire, and we assume that everything is going to be consumed, that there's no evidence left behind for us to see. However, in reality, are our houses completely empty? No. What do you have in your house? You have furniture, you have a bed, you have a kitchen, refrigerator, table, etc. So these things can actually cover and protect some of the areas that may contain DNA evidence. So we'll use this pen to demonstrate what that looks like. So we have our paper on bottom again, but this time we have some fabric, a brick, and a stone that is sort of covering, there we go, our fabric. So as the fire burns now, if you go in, you would think, oh, everything is gone. Everything has been consumed in the fire. However, if I lift this brick up, look what's left behind. And if I lift the paper up, what's left underneath? Bits and pieces of our scene. And that's what we want to look at. Sometimes it's what's protected in a scene that we really need to go back and really evaluate in order to get our DNA profiles. With this, I would be able to go back, lift up the items, and see what was underneath, and possibly use that to help gather clues, to help solve the crime that we're investigating. So, I absolutely love my job. My job is fantastic. It's the coolest job on the planet. I get to light things on fire, I get to see what's left, I get to recover DNA profiles, and ultimately, we hope that this makes for a safer community. I encourage you all as you go through school, love, love, love your science classes. Embrace them. Sometimes they can be really hard, right? They can be really hard classes. But ultimately in life, it can help save your community. So thank you very much for your time today.
All right. By the way, how many of you have noticed the pattern of our presenters saying they have the best job in the world? We did not plan that. We did not ask them to say that. But it shows you what happens when you follow your passion, when there's something that you're truly interested in that you want to turn into your job. So that was a little bit of lab work, and a lot of people love digging into the lab and looking at clues. How many of you are kind of more outdoors people, like getting outdoors? How many of you like animals? Yeah? How many of you like cuddly pandas? How many of you like fluffy kittens? Yeah, our next guy deals with none of that. He deals with things that slither, things that crawl. He's what's known as a herpetologist. A herpetologist. So I want to bring out now from the Staten Island Zoo, so names I've been blanking out on today. It's horrible. I've been studying them all day. But look, it's going to come up. Oh, there he is. Yeah, Matt Lanier, please. Welcome.
Great. How's it going, guys? Thank you, Bob. Appreciate that. I want to say it's great to be here. Really having a great time today. Just a little background about myself. As you can probably tell, I'm not from Brooklyn. I'm from Tennessee. Growing up in Tennessee, I was fortunate enough to have a creek running through my backyard. So I was always outdoors, getting dirty, in the woods, flipping rocks, bringing snakes home, much to my mom's dismay. She didn't like that, at all. I think I was in the 4th grade when I heard the word herpetologist, and I really understood, like, wow, you can actually do a lifelong job and work with the things that I've been going out and playing with this whole time. And that was great. I just loved it. So I went to the University of Tennessee, and I graduated with a degree in zoology. After I graduated, I actually worked for the University of Tennessee for about 5 years in a reptile ethology lab. Now, the word ethology, that means behavior. So we were checking out different types of behaviors for different types of reptiles and all that. So I've brought some friends here today to show you guys. So enough about me. I want to introduce you to a couple of friends here. And this is Carrie Gallagher and Samson. Carrie is the human. Samson is the tortoise. Carrie is our director of education at the Staten Island Zoo. So let's all check out Samson here. Now, Samson, he's 20 years old, and he is an African spur-thighed tortoise. And you can really come, I tell you what, if you want to get up here close, a really good shot, we can check out some of the really cool adaptations that this tortoise has. So you can see he is a vegetarian. So I don't know if he's really hungry at the moment, but where is vegetation? In trees. That's way up top, in the branches. How is a tortoise going to get to that vegetation? Is he going to climb the tree? Absolutely not. So what they are able to do, these guys are great diggers. They can actually uproot a tree and send the tree toppling over, where they can then go around and climb up and get some nice greens. But I guess we just don't want any greens at the moment. No big deal. Guess what else they can do? Africa, of course, really hot, right? Oh, you hear people say, oh my gosh, it's Africa hot outside. Well, wild reptiles do like actually the heat. The baking hot sun heat of the day, it does get a little too much for them. So what they are able to do is dig, and they can actually dig burrows up to 10 feet long, 10 feet down into the ground, where they can climb in there and they can escape some of the heat. Another really cool thing, you got a prop for me? Let me see this thing. So these guys, they hatch from eggs. And guess what? This is the size of the egg that he hatches out of. Like I said a minute ago, he's 20 years old. He can live to around 80. So he's got some more growing to do. But when they hatch, this is about the size of the egg that they hatch out of. Pretty crazy, right? All right, Carrie. Thank you very much. I appreciate it. So I'm going to give you Samson back here. Got him? Very good. We'll clean this up a little bit. Thank you. So I just want to tell you a little bit about what I do on a daily basis. We have around anywhere from 250 to 300 reptiles in our collection at any given time. Mainly, I deal with the venomous snakes, cobras, rattlesnakes, gaboon vipers, Asian pit vipers. One thing that I just love about my job is every morning I wake up and I know I'm going to work and it is going to be completely different than the day before. No matter what happens, it's always going to be different. And you've always got to kind of bring your A game when you're dealing with a 9-foot cobra that kind of could come striking at you at all times. And you need to know the different personalities. You need to know the different mechanisms on how these guys can actually work and move. So now I'm going to go get our second friend. Hey, Carrie, you want to get us some volunteers? We need a few volunteers here. All right. Come here, little buddy.
Hi, guys.
Volunteers. Go.
Hi.
Hey, guys. All right.
Hi, how are you doing?
So now we have an African dwarf crocodile. Let's get another close-up. How about that? See those crocodilian teeth? And see those big eyes? Those are for seeing things in the dark. These guys are night hunters. Very good. Excellent. So he is kind of small right now, right? He's only about 2.5 feet long. He is 4 years old. His name is Nero. He is what we call an ambassador animal, so he's used to going out and meeting people, so don't worry about that. He's going to be a nice guy for us. So at his adult length, he's going to get about 6 feet long. So you might be thinking, now wait a minute, 6 feet, that's kind of big. That's not really a dwarf, right? Well, in the crocodilian world, that is. So let's see exactly what a 6 foot. There you go.
Take that in. Go that way. All right, there we go. Okay, and stop.
All right, so there you go. That's about 6 feet.
We're going to back up
to that red bandana. That's pretty decent size, right? And that's still considered a dwarf. And the reason that is considered a dwarf crocodile is, one, he is the smallest crocodilian species. And two, this is a picture of a friend of mine, Ian, from LA, and he is next to a saltwater crocodile, which can get over 20 feet long. So in the crocodilian world, let's check and see what 20 feet long looks like. There you go. You've got that in.
That's it.
We'll go all the way to here. So
that's 20 feet.
This is 20 feet long. Now, don't worry. We didn't bring him with us today. So you don't have to worry about that. But now you can kind of see, why he is called a dwarf crocodile. Even though 6 feet is pretty decent size to a human, in the crocodilian world, not so much. Not so much at all.
Thank you for your help.
Very good. Thanks a lot, guys.
Thank you. Thank you very much.
Thank you. Carrie, I'm going to give you Samson.
Nero.
Nero.
You can let go of that rope there.
So, okay, we talked about some long reptiles. Anybody have any idea of another long reptile we could? Yes. Just shout it out. Snake. I heard snake. You guys are exactly right. Want to see a big, nice, long snake? All right, great. So, here we go. Our traveling container. And where's Mr. Cameraman? We're going to need him again. Come on over here. Come here, Jake. All right, there we go. So this is Jake, our boa constrictor. Let's get a good close-up of Jake so you can say hello. Hey, guys. Come on, there we go. Now you can see him. Smile, Jake. Show him all those nice teeth you've got. Excellent. So, okay, we're going to get him up here and lift him up for a little bit. Even though he's pretty heavy, he's actually just about as heavy as Samson. Oh, my goodness. Yeah. He is quite heavy. Now we can get a little bit better look. So Jake is another one of our ambassador animals. He is a red-tailed boa constrictor who lives in Mexico, Central America, South America. And you often find these guys in the pet trade, which is kind of unfortunate sometimes. Because you see them in the pet trade and they're about like this. And then you get them home, and if you care for them properly, in a few years, they turn into this. So you just got to be, you do have to be careful and research what you're doing. Research what pets you want. So I don't know about you, Carrie, but it's getting a little heavy. And for me, this is the best part of my job ever. I don't know. Just interacting with these guys. I know you interact more with people.
Yep.
I seem to do better interacting more with reptiles and cold-blooded things.
Yeah, Matt thinks he has the coolest job because he gets to take care of all these animals every day, and that might be true for him. But I think I have the coolest job because I'm on the other side of the glass, and I get to take the animals out and talk to the public and teach people about conservation. So my science is conservation biology, and I use that with a little edutainment and try and teach people about why these animals are so important for the world and for every ecosystem on the planet. But he is getting heavy.
He is.
So maybe we can get some help from those other scientists.
Get a few help from some guys.
Where are those guys? Can't they help us out?
All right. Excellent.
Cool things about Matt's job? Yeah, give it up. That's it.
You want all of it? You got it? All right, cool.
These are great jobs. Like dinner conversation.
A little bit of a right? Very strong.
Imagine you go to a dinner party and people are like, oh, what do you do? Venomous animal handler. All right. Well, listen, a big hand for all of our cool job participants. Amazing.
We're going to put it back.
Now, for those of you who might know, I have a cool job too. I'm a teacher, which is an awesome and cool job. And occasionally, I also get to blow things up on television. Now, of course, this is not a television show, but I did see someone with an iPhone. That's close enough for me. Is it all right if we do a little science demo here? Is that all right? You guys are up for it? Yes. All right, awesome. So let me introduce you to a little powder here. This is called lycopodium powder. It's actually the spore of a little club moss that grows in the forest. This is what it looks like. It's not particularly exciting. And if I were to try to light it on fire, yeah, not much going on. See? So it's kind of harmless. And in science, I say that anything can be harmless and anything can be dangerous. Water can be dangerous if you don't know how to handle it, but it can also be harmless. So just in the bowl, this is harmless. But if you were to aerate it, if you were to put it into the air and surround it with oxygen, then it can take on a very different kind of flammability factor. Would you like to see what that looks like? All right. So a long time ago, they would have these things called grain mills, and they would grind up flour, and the flour would often get into the air. Someone would walk into the building, light a match, for something, and the building would end up exploding from the flour in the air. That sounds incredibly dangerous, so I say we should try that. So we're going to kind of recreate that experiment. This is going to be sort of our grain mill here. So I'm going to ask all of our awesome scientists, go ahead and light the candle that's inside of that. That's going to act as our flame source. Now what I've gone ahead and done is I've added some lycopodium powder into the little nozzle in the back. All right, they've got that. You may now go ahead and put the top on. Make sure it's on there nice and tight. This is the roof of our grain mill. All right. Excellent. Well done. And grab the end of that tube and just kind of step back there. They've all got their safety glasses on. Excellent. So here's what we're going to do. I'm going to count to 3, and they're going to blow into the tube. That's going to send some of that lycopodium powder into the air inside of our grain mill. And we're going to see why you might not want to be in that building with a match. Are you guys ready?
Ready.
Oh, sorry. Before I do that, no, I'll tell you guys later. All right, here we go. Ready? And 3, 2, 1, blow! Well done.
not as full of hot air as the rest of us.
All right, if you thought any of these jobs were awesome, I'm happy to tell you that our incredible Cool Jobs participants are going to be in the lobby after this. So if you have questions, if you want to get up a little bit closer to some of those animals, they will be there to talk about it. Hopefully, we've inspired you, and hopefully maybe some of you will look at a job that you haven't thought of before. But either way, thank you for coming. Thanks for being part of Cool Jobs 2018, and we'll see you guys all next year.